the first one is linear, the second one is not. Okay? So how to solve it using a Kalman filter? How to make a Bayesian tracking? Because, I mean, when we started talking about the tracking of the target. And so what I come out here is that that tracking of the target, if you remember, when we started, I started to deal with this picture. This was the first picture I started. You see, this was the tracking of a target. And so when I made this picture here, where you know this is the a posteriori, then this is the a priori, which is is getting more uncertain. Then after the measurement, okay, the a posteriori here, the covariance is shrinking, okay. But what's happened? What I see there is that is not linear. So that's a bad news. Now, how to solve it? So the way to solve it is by using the Kalman filter and linearize the Kalman filter. So in other words, what I do is this. I mean, since this equation is nonlinear, okay, so I mean, what I can do is that I can linearize. So I can locally linearize the relationship. So this is general. It's general in the sense that I can always try to linearize either the state evolution and the relationship between the state and the data. I can linearize that. And so the linearization of the relationship is a suboptimal solution. It's a suboptimal tracking. It's not the optimal one. And so it's suboptimal linearizing. And you only do because you want to use a Kalman filter equation. Remember, linearity is always nice because you have a matrix multiplication. Even if for you the matrix time vector multiplication seems annoying part, but if it is linear, it is linear. It's much, much better. So anyway, so the way to do is the following. You linearize. And the linearize is called extended Kalman filter. So the extended Kalman filter is a Kalman filter when I linearize the relationship between the state, between the dynamic or the relationship between the input output. Now this is our case. So we have the data, okay, and then we have the relationship between the state and Rx, and so this one are the position of the receiving station. Okay, so it's okay. We said that. So anyway, now so how to linearize? In order to linearize, what I need to do, I need to calculate the gradient for that. So it's carried out simply in this way. So since my relationship, putting in a compact form, so it is R hat n, which is a vector, is equal to B, which is a nonlinear relationship depending on theta n, plus beta n, so, what I do, I linearize that. So which means, I can calculate, so this B theta n is approximately equal to B theta n minus 1, which is the state at the previous iteration, plus the derivative of B theta n with respect to theta n computed for theta let me write without n. This is more compact and more serious. Right? Calculate for theta equal theta n minus 1. So what I do, I linearize with respect to the previous iteration, then multiply by delta theta n, which is the vector. So this one is the gradient. But you know, it's a gradient now. Since b is a vector, since theta is a vector, is a gradient calculated between a matrix and a vector of a parameter and the vector of a known. So this gradient is a matrix. Is a matrix of gradients, which is what I indicated here. Okay. So, you know, what I do in a Kalman filter is that I linearize the input-output relationship, and then by linearizing, okay, I approximate, this is the linearized part, so I approximate my non-linear relationship with a second part, so this one is a linearized one, and this one is a correction term. So this correction term, which is a b, which is, you know, the linear part, minus the linearized one, which is, this is a linearized, and this is theta hat, which is a linearized. So in a Kalman filter, what I do is I substitute into the Kalman filter the linearized equations. Now, in this way, I can use the Kalman filter. I can use the Kalman filter for linearized tracking. Now, made in this way, the Kalman filter is not optimal. And the extended Kalman filter is not optimal. The other strategy could be that you implement a fully nonlinear system, which is something that you might do for tracking. No, so, you know, if you don't want to linearize, you can use the fully nonlinear filter. Now, what is the way? I have a set of remarks here. Okay. Let me go. Now, if you don't want to use the extended Kalman, you can use the so-called non-linear, non-Gaussian probability density function, which is involving non-Gaussian PDF, and then you can use several methods. We are not touching. It's not part of our course, but you know. These methods, I mean, one of the most, let me say, most popular in these days are the particle filtering. And the particle filtering is just a way to represent a non-Gaussian distribution by a set of particles. And then, you know, what I'm saying is that see the particles, so, you know, you go to the web page of my colleague and you get the corresponding particle. Now I have a set of comments here that I know I skip because I want to move to make a couple of examples, couple exercises. Okay, you can read yourself. So check these remarks. You can check them. Now, going to the exercise, I selected here. Now, I leave this because I leave to you this one because it's on maximum likelihood. Okay, so these are the exercises that I selected. So this is on 16 July. And this exercise is on maximum likelihood estimation in multilateral. What is that? It is the story that I'm not tracking. I'm estimating the position of the target by using a single measurement. There is no tracking here. Now let's read the exercise together. And you have to solve it. You have everything to solve it. So it's something we already did. Except the frame of work of the problem. So the problem is slightly different from the conventional one. Now, let's read it together. The position of one point, Rx, Ry, in 2D, as in figure, here. Okay, that's the problem we are solving. So there are 3 stations that are receiving the signal by this point. And so I can estimate the time of delay. From the time of delay, I can get R1. R2, R3. Okay? So let's read it. Now, the position of one point, as in figure, can be estimated by multilateration as a combination of the time of delay estimates, tau hat. So I have the tau hat, which is tau 1, tau 2, tau 3 hat. Okay, this is the vector of the time of delay. By the three receiver in the position of R1, R2, R3, where Ri is, is the two coordinate of the point. So that's our problem. Okay? So I have R1, okay, which is depending on two coordinate R2, R3. Okay? And then what I do, I estimate the time of delay tau hat 1, tau hat 2, tau hat 3. Okay? The point is characterized by Rx. See Rx or Y, I guess. You see? I see Rx or Y. Okay. So these are, the position of the point. And the position of the station are Rx1, Ry1, Rx2, Ry2, Rx3, Ry3. Okay. So what I need to do, the time of delay estimates, and then I have the three receiver position. Assume that from the point Rx and Y, there is one transmitter that transmits a triangle waveform with a time width Tg. So this guy is transmitting a triangle. So what's happened is that, each receiver, so let's say number 1, number 2, number 3, okay. The signal received by the three receivers, 1, 2, and 3, is a triangle waveform. The 1, 2 is closer, number 3 is far away, that's here, okay? This is tau 1, tau 2, tau 2. So I transmit this triangle. Okay, the amplitude is K, and this distance is Tg minus Tg half Tg half. Each receiver, it's long but it's easy. Each receiver receive a delayed waveform affected by propagation of acceleration versus distance, such that, so xit, which is the received signal, which I indicated here, is equal to A, amplitude of a transmitted one. This is the delay according to the distance, and this Ri square is the attenuation. Where V is 3 times 10 to the power 8 meter per second, is the propagation speed, the propagation velocity, and W is the white Gaussian noise with power, spectral density, and 0 divided by 2. Number 1. So let's start the exercise. Define the time of delay estimated for the propagation delay tau I and the properties. Okay? So question number 1 is on the time of delay estimation. I want to know what is the time of delay estimation in this setting. This setting is not different from others. So the time of delay estimation is as all the problems we did for time of delay estimation. Second, evaluate the Kramer-Rao bound for each of the 3 estimated time of delay in such a way that its variance is larger than blah blah Kramer-Rao bound. Now, this means that it seems this is for 3, but what I'm asking is evaluate the time of delay and Kramer-Rao bound, but the only difference is that I need to distinguish between R1, R2, R3. That's because R1, R2, R3 are different. Now, that's a new point. So, from 2A to B, I mean, you should go smoothly, except the framework of the problem, because I don't give you. This is the time of delay. This is the way for define the time of delay estimator, define the Cramer-Hall bound. What I'm saying is there are 3 time of delay estimation to do. There are 3 Cramer-Hall bound to compute. Actually, it is only a fake that there are 3 time of delay to establish, and there are 3 Cramer-Hall bound to establish because they are the same, except the scaling factor due to the signal-to-noise ratio. Assume I'm suggesting. So assume that the estimated time of delay are affected by zero mean Gaussian error. So the time of delay, the estimated time of delay is the true time of delay, and then there is the covariance D, where the covariance is diagonal. So it is sigma Cramer-Hall bound 1, sigma Cramer-Hall bound 2, sigma Cramer-Hall bound 3. Okay? Assume that where the covariance is coincide with the prove that coincide with the 2B. Okay? So it's a false question, this, which means I want that you show to me that since the 3 directions are referred to 3 different measurement devices, these 3 measurement devices are among the set themselves are uncorrelated. So because of the uncorrelation, the Cramer-Hall bound are disjoint, and then the estimated value have a covariance matrix that is diagonal. Now, suggestion 2A, 2B, and C computation can be carried out for an arbitrary receiver. Okay, so means keep a receiver wherever you like. Now, since the true delay depends on the unknown position of the point, evaluate geometrically the dependency of the time of delay versus the point position. Okay, so that means that the time of delay here. So tau, let me say tau I. So tau I, okay, is equal to, so it depends on the distance, so which is, no, I can't say. So it is C of V time the distance, and the distance is R minus Ri, which is equal to V square root of Rx I minus Rx square plus Ry I minus Ry square. Okay. See the theory today. Now, evaluate the maximum likelihood estimation for the distance, assuming that the tau hat is equal to that. Now, how do I make it? This is the true question for the exercise. So how do I make it? There is a linear transformation here. The distance, so the set of distance, so tau hat is equal to tau plus that. Okay. But now, what is tau? The vector tau is v times the norm. So tau, depending on the distance, is equal to v, then it is r minus r1 R minus R2, R minus R3. Okay, that's the distance. So, you know, these, the relationships are non-linear, because there is a square root of, okay? So it's V, and then you know it's square root of blah, 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 square root of blah, 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 square root of blah, blah. Now, what is the radius? So the radius, you know, is tau. Propagation, which is a meter per second, okay? So which means the difference radius, where is it? So the vector of, you know, of position of radius is equal to V multiplied by the tau. Okay, that's the radius. Now, since the delay depends on position, but there is geometrical dependency of the time of delay versus the position. Okay, this one is already down there. Evaluate the maximum latitude estimate for that one, okay, for R. Now, this is Gaussian, so I can say that, you know, this is the estimated value, and this is the tau, but you know, tau depends on the position of the data, and then I need to write, for solving that, I need to find the minimum, so the maximum latitude estimation for the Gaussian setting. Remember that my unknown is the position, so the maximum latitude is R min with respect to tau of, so I don't know, this time of the day, and then combine it. Okay, so I need to write, so it is tau hat, and tau hat is the distance so this one, so so it is the minimum with respect to that is, so it is tau measure, let me say tau hat minus tau depends on radius, which is that one, covariance d minus 1, and then it's the same, which since it is a diagonal, it is R min with respect to tau of the sum for I going from 1 to 3.
Sorry? But isn't that 1 over v instead of v times again?
Oh, you have the 1 over v, right? But you know, it doesn't matter here because it's scaling. Then tau hat I minus so it's 1 over v, say it's R minus R I square That's the maximum luxury. Divide by, okay, so these meter per second. Now I need meter. No, I need the second. Okay, divide by. You're right. You put me in the dimension in the right position. I need the map on that. Okay. That is the maximum luxury for that. So, I take the estimate of the time delay and then put in relationship with the distance, with the relative distance, which is by, by writing the maximum luxury in the general form. And then, using the Fisher information matrix formula number 1, see the reverse page. Compute numerically the Kramer-Rao bound for the case of the point in the origin, which is in the center, and thus the Kramer-Rao bound, so in D is all the same, and the distance between any pair of receiver is 100 meters. So the distance here, there is 100 meters. The target is in the center. Okay. So what I need to calculate is the Fisher information matrix for R. Now to solve that, I need to use, for this last point, I need to use the formula, which is, for the Kramer-Rao bound. But what I need to use, I need to find that what I'm doing is a transformation variable, which means I go from tau to distance. So this vector of tau is equal to 1 over b, then is a vector of distances. So assume that I know the Kramer-Rao bound on tau. My goal is to get the Kramer-Rao bound on R. So this is a change of variable between tau and R. So I'm using now the formula, which is, is describing how to calculate the Kramer-Rao bound on tau, how to get the Kramer-Rao bound on R. So it's a transformation variable. Okay, for this. Okay. So, I'm using the maximum luxury to solve the exercise. There is no tracking here. So the complexity of the exercise, we say, is that in this exercise, I play between time and distance. So this is the essence. I have tau and I have position. Okay? And then this is put in relationship with respect to R. So if I know the variance or the covariance of tau, how can I get the covariance of R? So in order to put these two that are one in function of the other in a relationship, so if I want to put them in the relationship, then I need to say that the covariance, if I know the covariance in tau, then the covariance in tau is put in relationship with respect to the linearization of tau with respect to r. Then I have the covariance of r, which is what I want, time the derivative of the tau with respect to r. This is the response. So, once I know the covariance of tau, I can get the covariance of r. Okay? And this is what the last question is asking. What is the covariance of r? Now, what you can find, this is a 2 by 2 matrix. Huh? And so this in this position is the variance of Rx. Here there is a variance of Ry. And here there is a covariance between Rx and Ry. Which means, if the corresponding, let me say, ellipsis is orientated this way, then the covariance between x and y position is 0. If the ellipsis is oriented the other way, the covariance between x and y are different from 0. So according to the geometry, which is there, what I expect that, the might be a stop. No, it's not a stop. So it comes that the covariance should be kind of elliptical. So probably is in that direction. So it might be that the covariance is 0. This can be computed. I didn't compute that. We might compute and then you can tell me. Probably compute in the book. Now, let's see another. Same exercise. Okay, so 8 February. Provide a short 2 pages description of a common filter and basic assumption in derivation. Now, since the equations are at the back of the text, these can be freely referred and not considered as a proof. So what I'm saying is that, give a basic assumption of derivation. So, I'm asking to derive, but I don't consider as a proof that you derive if you copy the equation on the back. So, if you just copy it, it's not considered to be solved the question, okay? So we want to know what are the basic assumptions. So the basic assumption is the one that we discussed. So linearity, Gaussianity, okay? And prediction, and the assumption of prediction, and the assumption of the update. Now, second, same figure. Specialize the Bayesian tracking in A, here, to the case of position tracking to the E in one single target with coordinate Rx and Y, here, this guy here, assuming that measures are gathered from 3 sensing points, 1, 2, 3, as a vertex of equilateral triangle, okay, same length on all sides. Measurement noise is independent on distance, and the evolution of the position is modeled as a first order Markov model with blah blah. Okay, so you see, this representation is exactly the one that I was discussing before, saying that I can use a state as a state of equation, not just the position and the speed, but only position. Okay, so that means that these are the states variable, and then what I'm asking you to do is to put into the relationship with the R1 and R2 and R3n. Again, square root of, square root of, square root of. Okay, specialize the case. That's all that I'm asking you to do. Even if it was so simple, it was a nightmare. Okay, so most of you solved the first, but never, almost, one or two solve the second one. What I'm asking is put it in a frame it in a way that it's fulfilling the conventional common filter assumption. Okay, so I mean this exercise, so this one is C through the theory, and this one, you know, is just reframing the positioning. Okay, as indicated. So that's easy. Okay. Common filter for time varying filter. Now let's read. The linear system with impulse response with index and length 3 is time varying over index k. So k is the variability of the filter according to the model. Okay. So you know it's hn 1/2 hn k minus 1 plus alpha k. So looking there is this way. H is 3 samples, so it's H0, H1, H2. The estimation and tracking of the time varying impulse response is by exciting the time varying filter with the unknown signal represented here by a sinusoid with known frequency. Omega is equal to pi. So the excitation is xn is equal to sine omega not time length. Measurements are modeled according to the block length and filter response as this. So this is the input-output relationship, and that is the evolution of the state. Okay, so we know everything. Where noise is zero, mean white, Gaussian, blah blah blah, with power, blah blah blah. Okay, so I mean along the text to say that this is the first equation that I need. That is the second equation that I need, and this is the property of the excitation. So, now, that means that the excitation here is the property of the excitation, which is a training that goes there. Okay? Now, describe the system using canonic dynamic model. Detail where the estimated pulse response is referred to the measurement model. 0, 1 here, this, okay. Which means frame it into the conventional common filter model. Evaluate and motivate whether the common filter or the standard common filter is applicable to this case. Now, is it common filter or standard common filter? Is it non-linear or linear? I have a training. I know the training. What the noise is 0 mean white Gaussian process with power blah blah blah. Alpha is blah 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 blah. So the filter is common. Okay? The problem is framed as a common filter. Okay, now sketch the common filter or extended common filter based on B by detailing the most specific adaptation that are necessary of the standard theory and equation. See attached formula, which means, you know, look at the formula on the back and use it in this case. Okay, so the main adaptation is the following. H is theta, the state, okay, and this is the state, and so you know the main adaptation is the following. So H n transpose x n plus w n. This is the main adaptation, okay? And this is theta. Now, okay. Now, if the filter response, this is D. D is the most difficult, okay? So, you know, it's always increasing difficulty. So the filter response is much longer than 3, as here. Say 100 or even more. So, very, very long filter. What could be the drawback of the measurement model 0, 1? So what could be the drawback here for the Bayesian estimation of the filter response? So you have a filter that is very, very long. Okay? And you know, and I ask you to look at the formula number 01, which is this one. What do you see here in this formula? Remember, I have a sinusoid. Okay? So I have a sinusoid which is filtered. My filter composed with 3 coefficients, plus nodes. So if the filter is very, very, very long, what do I get as y? You know, it's that the filter is I am filtering a sinusoid. You know, the sinusoid that I'm using as a filter is periodic. That means that in my sinusoid I'm using, you know, a signal that is 0, so it's pi 4, pi half, pi 4, 0, pi 4, pi half, pi 4, 0, okay, and so on. So if it is very long, I'm using a sinusoid, and the sinusoid has all the coefficients that are the same. So if the filter is very long, I am exciting. So let me say, I'm taking, this is the signal, then you know I have the filter. But you know, this coefficient is equal to that, is equal to that, is equal to that. And I want to estimate this coefficient, this coefficient, this coefficient. But you know, all these 3, 4, 5 coefficients are excited by the same values. So that means that, you know, I cannot distinguish this coefficient from this coefficient from this coefficient, because the training sequence does not give me the possibility to sense the different coefficient of the filter. Okay? The control people call is not observable. Okay? So I cannot observe, since this is not a control exam of control. Okay? So I'm asking your intuition to see that I have a certain ambiguity, because the training sequence are putting together samples that are far away. Let me put it another way, in other words. If I have only 3 samples, you know, this is for the 3 samples, so you can see the recording, so you can reason that. If I have 3 samples, so you know what I'm doing, I'm looking at these 3 samples, okay? Now, you know, it's evolving, so these 3 samples are changing, okay? But they're always one different from another. So, what is a convolution? Convolution is taking samples number 1 multiplied by coefficient of the filter 1, plus number 2 times the filter 2, and plus number 3, the filter 3. Okay? Then I get the output. Okay? Now, what is for if it is that long? Then you know I take these samples, multiply by the input, plus blah blah blah. But you know, I also have these samples plus the input, but these samples plus the input. Now, when I'm shifting, I have these samples plus the input, these samples plus the input, and so on. So what's happening is that I cannot distinguish, because I mean, in my formula, I get a sum of terms that are always the same grouped together. So that means that I cannot estimate properly sum of the coefficient of the parts. They are not distinguishable. They are not observable, right? I mean, it's not. We are not doing control exam, so you know, I'm triggering your intuition on that. Okay. Okay. I remember, you know, during when I corrected, there was one I was saying, it's there are some of them are similar, but they are multiplying, they are combining same coefficient. For me, it's perfect, you know, because he understood what's happened. You see, So when I ask you this part, I don't want exact answer. If you have the exact answer, fine. But I want to see how you elaborate on a different topic, which is not exactly what we covered, but you can easily combine all your knowledge related to the course to put into an answer or to understand what's happening. That was my goal. That's it. Tomorrow we finish the spectral analysis that we started Saturday, and we had exercise at the bottom on the periodogram, because the periodogram is always a little bit complicated, okay?